Nicolo, are you ready?
Yes, I am.
Okay. Then, ladies and gentlemen, this is the second lecture of Nicolo, talking about learning theory, and the stage is yours.
Thank you so much. Welcome back, and thanks for being here early in the morning. And so I'm gonna continue the analysis of the problem we were looking at, which is this problem of prediction with expert advice and bandits in an online learning setting. So I remind you just that we had D actions that the learner had to choose at each time step. And the idea is that every time you chose an action, you would incur the loss of the action you chose and observe both the loss of the action you chose and that of the neighboring actions in a graph. And the graph is given, and in this way you can interpolate between problem of full information, like in the expert setting, and problems in with the partial information, like in the bandit setting. So the idea is that we were going to use these exponential weights with loss estimates, and the loss estimates were designed using this importance weighting scheme, which every time we were able to observe a loss, because it was the loss of an action in the neighborhood of the action we chose, we divided it by the probability of observing it in order to compensate for the fact that whenever we didn't observe the action, we gave it a loss of 0. So we computed very quickly that these estimators are unbiased with respect to the probability, with respect to the randomness in the choice, internal to the algorithm, and the randomness of the algorithm in choosing the actions, and has also bounded variance. So the variance is bounded by the reciprocal of the probability of observing the action. So this is just because we chose this specific design for the loss estimates. So now we can do very quickly the regret analysis. So you remember we wanted to, in the regret, we want to bound, let me go back somehow, probably have to go back a long way, yeah. So we want to bound this difference, which is the expected cumulative loss of the algorithm with respect to its own randomization, with respect to the expected cumulative loss of the best single action in given the deterministic arbitrary assignment of losses to actions. Okay, so how do we do this? It's actually pretty easy. First of all, you recall, so probabilities are just exponential weights normalized. So this is the normalization. And we can call this exponential weight, for convenience, we just call it WT of I. So this is the weight assigned at action I at time t. It depends on the past estimated losses. So now we look, in order to do the regret analysis, we look at the evolution of this ratio, the ratio of weights over time. So we can just open up the numerator. The numerator, it was just the normalization constant, so it's the sum of weights, okay? And then we can sort of split it up, because we know that the weight at time plus 1 is an exponential up to t. And we can extract the last term from the exponential, and it becomes a factor because it's a sum at the exponent, so it's a factor at the base. So we pull out the last loss at the exponent as a factor, and now this ratio here, we recognize it just being the probability of time t. So we have that. And now we can just, expand the exponential using a very simple quadratic upper bound on the negative exponent. Okay, it's a negative exponential, so it's pretty easy. Estimated losses are positive, so negative exponential are easy to upper bound. And we get to this upper bound, and then we just move in the probability. So this remains a 1 because it's sum of a probability, and then it gets into there. So we get this upper bound on this ratio of weights. Very good. And now what we do is just, we take logs and we sum over t. So at this point, you see, if you sum over t, if you take logs and sum, then it becomes a telescoping sum, because the log of the ratio is the difference of the logs, and it telescopes. So at the end of the day, you get that. And then you just massage using this very simple upper bound on the log what you had on the right-hand side. So it's a super simple algebra. You can look back and convince yourself that is an easy step. So now we have an upper bound on this ratio on the log of the ratio between the last total weight and the initial total weight of our algorithm. So what is now the last total weight? Well, we know that this is the last, so this is the sum of the final weights of all the actions. So we can just pick one of them, say some fixed action, which will be the best action for that sequence of loss. So we call K the best action for the actual sequence of losses up to time t. And so it's a sum of weights, so we just pick one term. And okay, so this is an exponent, so we can just, the log of the exponent, it becomes just what we had at the exponent, which is the negative sum of estimated losses. So the initial weight, so at the beginning, the weight, okay, what is the weight? The weight is the exponent of a cumulative loss. At the beginning, the cumulative loss is 0, so e to the 0, 1. So initial weights are all 1. So this is the sum of d1, so which is d, so we get minus log d in this over here. So we have now an upper bound on this ratio, log of the ratio, and the lower bound on log of the ratio. We put them together, and we divide both sides by eta, which is our learning rate, bigger than 0, and we get this expression here. So now you can, okay, we just repeat it here. Okay, so we are here. So what we want to do is now, okay, this is actually holding for every we didn't use probability here. So this expression, this inequality is holds deterministically whichever are the choices of our algorithm. So whichever sequence of actions our algorithm chooses, this inequality is gonna hold. And remember, these things are random variables, okay? Because they depend on the actual realization of the algorithm choices. So loss estimates depend on what we observe, and what we observe depends on what we choose. So now we can take expectation with respect to the sequence of choices of the algorithm. Okay, so we can just write expectation at the outside. This is deterministic, and we can take a write expectation at the outside, and we can write conditional expectations in the inside. This is just using the Tower rule of expectation, some very simple probability property of expectation. Okay, so now you remember that, so we now took expectation with respect to the randomization of our algorithm. So we are looking something interesting here. So we want to get now something meaningful. So first of all, we observed that we had this unbiasedness property for loss estimates. So these expectations are just the true losses because we computed those, okay? And now look here, what do we have here? Well, this is just a regret. So this is the expected cumulative loss of the algorithm with respect to the probabilities that the algorithm was using to choose the actions, compared with the cumulative loss of the best action. Okay, so this is just definition of regret. So this is actually a deterministic quantity, so I could have moved the expectation, kept the expectation only on the first term. Okay, so here we have the regret. Here is an upper bound. So all is left is to control the variance of our estimates. And remember, the variance is just the variance induced by the internal randomization of the algorithm. There's nothing, there's no probability outside. Okay, so we're back here. So we want to control the variance. We compute the upper bound on the variance, that it is. So P, you remember the upper bound on the variance was 1 divided by the probability of observing the loss. So we get something like that. We used our variance bound. And now we can write the probability of observing. What was the probability of observing? You remember, we can observe the loss either if we pick the action, which happens with this probability, or if we pick an action which is in the neighborhood of that action I. Okay, so, and this happens with that probability here. So this is a sum over the vertices of a graph, which are our actions, of some probability assignment to these vertices according to this pattern. Now, this is something that has been studied actually in graph theory. So we can use this gram theoretic result and upper bound, this sum over here, it says actually is a cool graph theoretic fact, and is not hard to prove. For any assignment of probability over the vertices, if you sum over the vertices these ratios, you can upper bound with the independence number of the graph. Okay, so this is just a probability, a graph theory fact. There is no magic, and it holds for any probability assignment. So just to remind you, what is the independence number? If you have a graph, the independence number is the size of the largest independence set, which is the size of the largest set of vertices that are not pairwise adjacent. Okay, right? And so our regret bound now can be written like that. And by tuning the learning rate, I can write the upper bound like this. Okay, so let's try to make some sense of this. First of all, we can observe that this bound is tight for all graphs. So up to logarithmic factor, we cannot, for any single graph, observability graph, we cannot improve on this bound. And second, as special cases, we recover the bound I claimed for the experts, and actually we recover it up to constants. Because this is a sort of more general result. And the reason why, the reason for that is that the independence number of a clique is 1, because every two vertices are adjacent. So, and in the case of the edges graph, which is the bandits, the independence number is D, because all the vertices are non-adjacent. There are no edges. And so I have these two upper bounds. So this was the non-upper bound for the edge algorithm, and this was the non-upper bound for the XP3 algorithm, which is the special case of the algorithm that I showed you before, the exponential weights algorithm with the loss estimate, when you run it on a graph without edges. So, and for any other intermediate observability model, you get a bound that interpolates between 1 and D as terms. As if you think about it, the presence of a D factor here makes sense, because in the case of expert, we, at the end of each round, we would observe the loss of every action. In the case of, and these are D many actions. And in the case of bandits, we observe 1/10 of that information, because we just observe the loss of the action we play. And that's the reason why the variance, which was 1 here, blows up to D here. But still, the dependence over time, which is the important thing over here, remains unchanged, which is pretty amazing considering the fact that you have a whole range of partial feedback information here, going from full to all the actions to just one action. Okay, so this is a sort of a nice and crisp setting for studying the effect of partial information in online learning. And the analysis is, as I said, is very simple, but still is pretty general. So you can account for a wide range of partial feedback models and relationship between actions. So there are more general results that I will skip in the interest of time. So you can also consider directional information, like in the revealing action case, in which if you play this action, you observe all the losses of all the other actions, including the action you play. But if you play any of these actions, you don't observe anything. So you can actually deal with this kind of even more general feedback information. And essentially what you observe that you have different regimes for regret. And in the case of revealing action, so in the case of in this kind of feedback graph here, you have a decrease of your regret from square root of t to t to the 2/3. However, there's a nice gap theorem that tells you that whichever graphical feedback model you consider, your regret is gonna, in terms of the dependence on t, is gonna fall in one of these three categories. And you can actually classify all the graphs very precisely in these three categories. So if you give me some observability graph, I can tell you how the regret will depend on time just by looking at the graph. Okay, so this is an interesting characterization. And I mean, I believe because it's very simple, but is tell you something about the interplay between the amount of intervention you observe and the kind of the regret you can obtain in this online decision-making game. Okay, waiting for some questions. If not, I want to move on. Lisa will come back.
Just a second, there is a question.
Very good.
Can you see it? I can also read it out.
I don't see it in the Q&A.
No, it's in the chat.
I don't see it. I don't see the chat now.
So at the bottom line, there's the participants, and then next to the chat.
I know, but somehow I don't see it.
Okay, then let me read it out.
I don't know why, but it went away. No, truly.
Okay.
Let me see if it's, sorry, maybe. Oh, come on. Everything.
Oh, probably you can read it,
Check,
or I can read it.
Yeah. I was just waiting if he finds it. So then let me just read the question out. So.
The quantity, I get it.
Yeah, go ahead.
Yes. That's an excellent question. And I will come back to that. Because this analysis I show you is a special case of a more general analysis, and the more general analysis has to do with the general online convex optimization setting, which I'm going to talk about it now. So in this is a special case of the more general analysis. So as I said, right, I introduced this bandit game and this express game as a sort of an online learning game in a simplex. So you bet using a probability, your decision is a probability distribution over the actions, and then your loss is linear. But we introduced our online learning framework was a lot more general, right? So now I want to see whether I can take these results and lift it up to this more general framework. So here is the slide I showed you at the beginning when I introduced this online learning framework, coming from the traditional statistical learning, right? So now I want to say that my model space is actually a parametric model space, which is some convex closed non-empty subset of the d-dimensional Euclidean space. And I want to say that my decisions, my models are vectors of parameters from this subset. And my loss is going to be some convex loss, which is a convex function of my decision, which is this point in this d-dimensional subset. And then I will use, as information, I will use the gradient of that is a first order oracle, because I want, as I said, you know, I'm learning, I'm interested in doing a cheap and quick updates. So first order information is, these are D numbers, which is just a gradient of the loss, of the current loss at the played point. And so this, I will assume I have this information as feedback. This is exactly what I get in the case of the linear loss in the experts game. So in the experts game, I would get the coefficient, the d coefficients of my linear loss, which corresponds to the gradient, if you think about it. So this is actually compatible with what we studied earlier in the experts game. It's full info because I see all the components of the gradient, and I'm not insistent on the fact that my loss is linear. I'm just saying it's convex. And I'm not insisting on the fact that V is simplex. It's just any convex closed subset, okay? So that's the generality. Convex losses, arbitrary decision spaces. Arbitrary meaning that subset of the d-dimensional space. Regret is defined as before. I'm comparing the loss, cumulative loss of the sequence of my decisions, of the algorithm's decisions, to the cumulative loss of any decision in the set. In particular, I'm interested in competing with the best decision for that sequence of losses. So sequence of losses, though, is a sequence of loss functions. They are convex, but it's absolutely deterministic. And for now, I'm looking just a full information setting, okay? So I'm observing all the components of the gradients. Very good. Everything is under control. Q&A, I see Q&A, and I see the chat box, so you can ask questions. Okay, so I told you that this what is the generality? What is the payoff for studying things with this generality? Well, you can do a stochastic gradient descent using online learning. So in stochastic gradient descent, you want to minimize training error. And so you have some training set of points and you have some loss, maybe, you know, the square loss of the entropy loss, whatever you like. And you want to find maybe approximately you want to minimize, and maybe you won't be able to find, maybe this is not convex in W, but you want anyway to use some gradient descent procedure. And the idea is that maybe you have a huge training set, so you want to use, you cannot do a global optimization, you want to use a stochastic method. And so what you can do is you can only, the training set is so big, you can only spend a constant time on each data point. So that's a perfect scenario for online learning. So you create a stream of convex losses just by sampling uniformly from the training set and by constructing a convex loss function using the data point that you sample from the training set. This creates a sequence of convex losses induced by the training points that you sampled, and you can feed those to your online learning algorithm. In practice, maybe you want draw just a single point, but you will use a mini batched approach. But in essence, you are still using an online learning philosophy. And you can, in the case you have some convexity property here, you can even use the online analysis to draw conclusions in terms of the convergence of your stochastic optimization procedure. So there are certain algorithms like Pegasus for minimizing the SVM objective, which are exactly derived from online learning analysis. Okay, so that's so besides having a genuine streaming learning problem, you can construct a streaming learning problem just because you cannot run a global optimization algorithm on your data set, which is too big. Okay, so that's another viewpoint on the reason why you should be using online learning in these cases. All right, so I want to start with, again, with some lower bounds for this more general online learning problem. But let me cut a little bit short. So the philosophy of this lower bound is similar to the one we proved for the experts case. So in this case, what I want to do, essentially, I want to have I'm choosing a point which is chosen essentially using two elements in my decision space that are furthest away, because I want to introduce a dependence on the diameter of my decision space. And then I have just two linear losses that have this plus one or minus one switch. So you see, this loss is linear in my decision, which is a vector, but it's linear with a plus or a minus coefficient, and that's that's sort of the missing bit for the algorithm. I can do a pretty much a similar reasoning as I did for the experts case, and but just by using some. So at the end of the day, I end up with looking at the expectation of the absolute value of the sum of these signs. And this is something that I've been looking at in probability, and it's called Kinchin inequality. And in the sense, I can lower bound the regret for any algorithm with something that depends on the Lipschitz coefficient of my loss, the diameter of my decision space, and the square root of the time. So the square root of the time is still, you know, this thing that is coming back all the time, and it's telling me that this is the best regret rate I can hope for, and I should also have these other dependencies that now, you know, tell me are both on the loss properties, on the decision space properties. Okay, so please do remember this lower bound. I use a stochastic argument for the lower bound, but then I will match it using a completely deterministic framework, the online learning framework. So let's now think about this lower bound a little bit. So one simple case is that my decision space is a Euclidean ball. This is a very standard case. And maybe my loss functions have bounded, have the infinity norm of the gradient bounded, okay, bounded away from 0. So I have, maybe they are, you know, constant. So the gradient is a vector with the constant size of the components. And the previous lower bounds now assumes, okay, if I translate these assumptions and if I put them back in the previous lower bound, this suggests that in such a situation, any algorithm should suffer a regret which scales with the square root of the number of dimensions and time, okay? And this, whenever my, decision space has diameter 1, so there's no dependence on the diameter, and this D is just because the gradient has D many components. Now, let's look at the different situation. Okay, now let's suppose we did this with the simplex. Now we can do also look at the problem of making decisions in the simplex, like in the express case, and using linear losses with coefficients that are bounded by 1. Okay, the loss components, the loss coefficients are between 0 and 1. And we know, because we did the analysis, that in this case, my exponential weights algorithm, which is called Hedge, achieves a regret for any point against any point in the simplex, which scales with that. Okay, this is a bit different scaling, right? Because the dependence on time is the same, but the dependence on the dimension is pretty much different. I have an exponential improvement when I go to the simplex with respect to the Euclidean ball. So somehow the geometry of the decision space matters. Here, basically my lower bound is telling me that I should suffer this much, but I have special cases like in the simplex where I have a much better dependence on the number of dimensions. So how is that? Okay, so somehow the idea is that the algorithm that you choose should exploit the geometry of the decision space in a clever way. And somehow exponential weights do that, because we know that this bound is optimal. For the Euclidean ball, the previous argument tells us that this lower bound is the best you can hope for, okay? So let's look at this in a more detail. So now we want to focus on online algorithm that use gradient information. So we start from something we know very well, which is just a gradient descent. So suppose you have some convex function that you want to optimize, you want to minimize. So you can, and you want to minimize this function over some convex set. So what you do is just you run your gradient descent procedure, because f is convex, and then you project your gradient step back in the set V, which is the set within which you want to minimize the function. Okay, so this is something, this is standard convex optimization. Projected gradient descent has been studied a lot. We know a lot about it. So we can write equivalent this in an optimization form. It's just an equivalent way of writing this. So we can write this as the argmin of W in the convex decision set of this sum of these two terms. So W times the gradient and the distance between W and the previous iterate in the optimization. Okay, so if you solve this optimization problem, you end up with something exactly looking like my projection here. Okay, so now we want to look at this optimization form, and we want to move to an online setting. How do I move to an online setting here? Well, I can take my gradient descent, projected gradient descent, and now I can pretend, okay, I don't have a fixed function, but my function is changing over time, because every time step I have a different function that I want to minimize. So I am doing a gradient step on the convex loss I am observing at time t. And then the next time I will do another gradient step on a different loss function, which is the one I observe on in the next time step. Okay, so I took my standard online gradient descent. I wrote it in a form that looks like that, which is equivalent to this one. And then I use the fact that I am in an online setting, so my function is not fixed, but is changing over time. And now I'm asking, can I analyze this algorithm? Can I obtain something interesting? But okay, so remember what I said before. I want somehow to exploit the geometry. So maybe it's a good idea is the fact that the distance between the previous model and the current model, which occurs in this minimization in expression I want to minimize in order to derive my next iterate, is maybe you know, in the case of the Euclidean ball, it really meaningful to use the Euclidean distance. But in a more general case, for different geometries of my decision space, for instance, the simplex, I should use a different notion of distance. So I want to make this more general, and I want to generalize the notion of distance I use to measure the distance between my models in the model space. And so if I do that, the projected online gradient descent becomes the online mirror descent algorithm, which is just online gradient descent using a generalized notion of distance as opposed to the standard squared Euclidean distance. So this generalized distance is called the Bregman divergence, and it's sort of a measure that generalized squared distance between models in my model space. Okay, squared because it replaces the squared Euclidean distance. So how do I construct these generalized distances? I start from a convex differentiable function from RD to R, which is called mirror map, for reasons that will become clear, hopefully, in a few minutes. And it's defined like that. Okay, this looks a little ugly, but this is just the error you make if you take a first order Taylor expansion of your convex function psi around W. Okay, so you're expanding psi of u around W, and this is the first order expansion of psi of u around W, and the difference between the two is the error you make the Taylor remainder, right? Okay, so since the function is convex, a first order approximation will incur some error, and the Bregman divergence exactly measures this error. Why is this the suitable thing to do? Well, if you take the squared Euclidean distance as psi, sorry, the squared Euclidean norm at psi, then your Bregman divergence become exactly the squared Euclidean distance. Okay, so it's a proper generalization of Euclidean distances. And now your online mirror descent becomes the gradient descent, which is the algorithm we were looking at before we generalized the Euclidean distance with Bregman divergences. Okay, and you just do gradient descent with Euclidean projections. However, you can take other things. For instance, if your decision space is the simplex, then if you take the negative entropy as your mirror map, which is a convex function because the entropy is concave and negative entropy is convex, then your Bregman divergence, if you do this computation, becomes the relative entropy or Kublak-Leibler divergence. And wow, then if I compute my online mirror descent using this Bregman divergence, if I do this argmin computation I wrote here, then what you end up is exactly, oops, super mess. It becomes exponential weights where at the exponent I have the gradient of the losses. Really? Yes, it is. If you do this computation exactly, you end up with exponential weights. So, okay, so this is actually what we saw before. This is Hedge, because Hedge was for linear losses in the simplex. And the coefficient of the linear losses is just the gradient, adjust the gradients if the loss is linear. So if the loss is convex, I should put real gradients on top. And then I have the analogon of my expert's algorithm for linear losses in the simplex, now for convex losses in the simplex. So just put the gradient of the losses at the exponent. This algorithm is called exponentiated gradient, and what you should be using if your decision space in the simplex. Okay, why? Because we know this is getting the right rate, the right dependence on the dimension in the regret. So we'll see this in a moment. So we'll see this in a moment. We'll come back to the special cases we looked before in a moment. But let me say a little bit more. So we want now to do the analysis of online mirror descent, and the analysis will be again simple enough, just a little bit more abstract. But it will be, why isn't this used for lasso in practice? If you want to run lasso online, you can do it. You can definitely use regularized objective. For instance, you can analyze the SVM objective in this way. Okay, so the question, okay, I think everybody reads the chat. Okay, so you can analyze ridge regression. You can analyze SVM, and you can analyze any. Okay, sorry. So someone asked why isn't this used for lasso in practice? And the answer was you can use this to analyze essentially any regularized convex objective, when you have a squared norm as a regularization term and the convex loss. And this includes SVM, ridge regression, and many other objectives. Okay. All right. So I want to use a specific set of mirror maps that are strongly convex. Okay. And this is just a property, meaning that essentially the function is a convex, is strictly convex in all directions, has a positive, as a non-vanishing curvature in all directions. Okay, if you take the function, you look at any single point, and you look around from that point in any direction, you will see a non-vanishing curvature. Okay. And we want this to be, and we measure strongly convexity with respect to a certain norm. And this is definition, and strongly convexity depends on a parameter mu, which will pop up in our analysis. Okay. And so this strongly convex mirror maps induce convex, your Bregman divergences now are always at least as large as these terms over here. Okay, that's a simple property to check. So if you have a differentiable mirror map, which is strongly convex with respect to the squared norm in this sense, then your induced Bregman divergence will have this property here. So you can sort of it behaves like a squared norm. Okay. Now this is a little bit trickier. Strongly convex mirror maps have some very convenient properties, so you can write your OMD algorithm in this convenient way. So you remember before we wrote it as an argmin, which is not very nice, because in order to make a prediction, you have to solve this optimization problem. But if your mirror map has this strongly convex property, then you can write it in this way. So how is that? So this is a little tricky. So first of all, psi is the restriction of my mirror map to my convex decision space, which means that I just declare infinity the value of psi outside of W. Okay, this is just a technical trick. And what I'm doing here is that I am using this other function outside, which is the Fenchel conjugate of my mirror map. It is defined in this way. And this is sort of a dual version of my function. Okay, this is something I can compute. So if you give me any mirror map which is strongly convex, I can compute the Fenchel conjugate. And this Fenchel conjugate, if the function is strongly convex, will be always differentiable. So now, right. And another property is that these two functions are functional inverses of one another. So let me give you just a picture to make sense of all of it, because this is a little tricky. But the idea here that your gradient descent, your mirror descent will look like the following. Okay, so there are two spaces. This is my my decision space, and this is where my decisions live. Okay, so now what happens? I have another space. This is the space of my gradients. Okay, this is where G is what stands for the gradient of my losses. And this is where I am adding gradients to losses. So somehow gradients gradients of losses are different. They don't belong to this space. They actually belong to a dual space of my decision space, technically. So that's why I am using some function, which is this gradient, which is translating between these two spaces. This is the space of the gradients of the losses, and this is the space of decisions, the coefficients I'm using to make my predictions. So I start from here. I map it using this gradient function here to the gradient of the mirror map to the gradient space. And then I do a gradient step. This is just a gradient step because I'm just doing gradient descent. I'm subtracting the gradient of the loss of the current iterate with the learning rate. And then I'm translating back to my decision space using the inverse of this function here. So as I said, these two functions are inverse of one of another. Okay. So this is why the reason why it's called a mirror, because these two functions are mirroring from the decision space to the gradient space. And the reason why I should use different spaces is because gradients do not belong to my decision space. They're gradient of losses. They are different animals. So, and these functions are translating between these two worlds. Okay, and this is this translation is somehow what is taking the way by which I take into account the geometry of my decision space. Okay, let's move on. So now I want to do the analysis. So here is the algorithm, and here's the algorithm how it works in the picture, and I'm using two inequalities. And once I have these two inequalities, everything comes out from first principles, which means from standard algebra. Okay, so one is trivial. What I do, I linearize the regret. Okay, you remember the regret is the sum of the losses I incur at every time step subtracted by the sum of the losses of some competitor in my decision space. Typically is the one that minimizes the sum of the losses, no? Because I'm always competing against the best model in my class. So now this is one term of my regret. And since losses are convex, and I can just do this upper bound by dropping the second order term, whose sign I know because the function is convex. So this is just trivially by convexity. I linearize regret, okay? And this is the gradient. The second is, I call it the Bregman progress. And this is something which depends on the properties of the Bregman divergence and on the definition of the algorithm, okay? So this is connecting these pieces here to this progress in terms of the Bregman divergence. So somehow Okay, you remember Bregman divergence measures distance in between models. So this is telling me how much by updating I moved towards U, which is the model, the best model in the class, the model I would like to compete against. Okay, so this is somehow is measuring the progress made by my update in terms of Bregman divergence. This inequality is not very hard to prove, but is somehow technical and just uses the property of Bregman divergences and the fact that my algorithm is written this way. This is just a super technical, there's nothing conceptual, but it's not that hard to prove. It's just a few lines. I will skip it. So we give these two for granted. This is trivial and this is technical. And now we look at the regret. Okay. And first of all, I linearize it. I just use this term by term. Cool. And then I use the Bregman's progress inequality. Okay, sorry, I didn't say what is this little star here. So I told you that my mirror map is strongly convex with respect to a norm. Okay. This is the dual norm of the norm with respect to the mirror map is convex. Okay, so we will see it's just another norm related to the mirror map psi. We will see concrete examples, but just think of it as a norm of the gradient. Okay, and the norm of the gradient has to appear because we already argued that it has to do with the Lipschitz constant of the loss. And we know this. We know through the lower bound that this has to appear in our bounds. Okay, so okay, we just use these two elements here, and we just copy the thing over here. So now we would like to telescope over this sum, but we can't quite telescope because there's a mismatch. So we can add and subtract a term in order to make this thing to telescope. And so let me just omit this that is just disturbing. So we replace it with a little square. So now I fix the telescoping. So I'm adding these terms, plus and minus these ones, in order to fix the telescoping here. And then I just do the telescoping. And then I'm left with some leftover terms over here, which are of this form. Okay, so this is again adding and subtracting, doing the telescoping, and dealing with these extra terms which I got because I fixed the telescoping.
Is there a question about this?
No, the choice of psi is predominantly V related. Yes, the choice of psi, yes, it is really related to the essentially, the geometry of the decision space will define the way you measure both the norm of the gradients and the norm of your models. Okay, so yeah, that's the explanation. Okay, let me finish this proof. So now we have now these things over here. So we telescope it. This is a negative, we can drop it. And what we can do, we can say, okay, this is essentially is the diameter of my decision space measured according to the Bregman divergence. Since the Bregman divergence is a squared distance, I'm calling it d squared. That's the diameter of my decision space measured using the notion of distance, which is suitable for my decision space. So I just put this there. So this, the sign of this has to be right. So I have some little assumption of monotonicity over here. Otherwise, I cannot do this upper bounding. But once I do the upper bounding, I can telescope this. And I do the telescoping, and then it's easy because I can cancel things here. I can cancel this with that. And then I'm left this with this, and the little square, which was this. So this is my upper bound. Okay, so now back to the question of Quan. Quan asked me whether this ratio of weights was central in the analysis. Okay, So if you redo this analysis, which analysis I just did, by using the relative entropy as a Bregman divergence, you will essentially recover the analysis I showed you for the Hedge exponential weights in disguise. Okay, so somehow the log of the ratio of the weights has a lot to do with the relative entropy. And you can play with that and actually recover the relative entropy. Okay, so the analysis I showed before was a special case of this one. And the idea is that instead of looking at the log of the ratio weights, I'm looking at relative entropies in general. Okay, so now I have this thing over here. Depends on the diameter of my decision space, depends on my learning rate, depends on the norm of my gradients, and depends on the coefficients of my mirror map. Okay, cool. And I can now choose my dynamic learning rate depending on the past gradients. This is something I will observe. I can measure these. These are my gradients. And I obtain an upper bound on the regret, which depends on the diameter and as the sum of a t on the square root and as the norm of the gradients. Okay, so this was, I hope was simple enough, maybe not too simple, but was reasonably simple. So let's look at special cases now. So we want to see how this mirror map in general can be matched to the geometry of the model space. And we look at these two cases. First of all, online gradient descent. So where the decision space is the closed Euclidean ball of radius d halves. And the mirror map, we take the Euclidean distance because we have Euclidean balls. So the Euclidean distance is an ideal partner. And this mirror map is one strongly convex with respect to the Euclidean norm. All right, no wonder, no surprise here. My Bregman divergence is, is the Euclidean distance. Everything is nice and dandy here. And I just assuming that, okay, now, this is not actually an assumption, sorry. The first equality is just a fact. The dual norm of the Euclidean norm is again the Euclidean norm. And I'm assuming that the gradients are of order of the squared gradients of size of order d. It's a sum of d terms, and I'm assuming these terms have a bounded, are bounded. So the infinity norm of the gradient is bounded, so the squared the Euclidean norm as order of d. Okay, and now here I plug in and get my bound. Okay, diameter and then square root of dt. And this is what I expected from the lower bound I showed you earlier. All right, so now let's look at EG. And here, my decision space is the probability simplex. My mirror map is the negative entropy, which is one strongly convex with respect to the one norm. Okay, this is important, the one norm. So I'm changing norm here. And this is important because, strong convexity, we are in the simplex, so one norm makes sense. Here's where it makes sense that it pops up. The Bregman divergence is the relative entropy. However, I have a problem because the diameter with respect to the relative entropy of the simplex is infinity. Because I have log of a ratio, and this is bad. Okay, if I get to the corners, I get infinity. Oh, wow. However, I can slightly change the previous analysis I showed you using a constant learning rate. So the price I pay for this fact, and that I'm forced to use a constant step size. I cannot use a variable learning rate as I did in my general analysis. If I use a constant learning rate, I can tweak my previous analysis and to show a bound instead of having the diameter of my decision space here, this is just exactly the same term, has the distance of my competitor Q with respect to the initial model. You know, the initial model is the first model my online learning process starts from. And I can pick this one to be the center of the simplex. And if you compute the Bregman divergence with respect from the center to any other point is upper bounded by log d, because the center is an entropy calculation. And if I make the same assumptions I did before, so that the gradient have, dual norm of the gradient. So the norm is the one norm, the dual norm of the one norm is the infinity norm. I'm saying, okay, fine, the infinity norm is constant, for the gradient is constant, which is the same assumptions I made before for the Euclidean distance. And then I get my beautiful square root of t ln d bound, just as a special case of my general analysis, with the only trick that I had to use a constant step size. So you see this, you see now the interplay that you have, and you see this is the question of Pierre Cyril. The question is that the mirror map has to be strongly convex with respect to some norm, and the dual of this norm is what you measure the number of the gradients against. Oops. And it turns out that, you know, for the simplex, you end up with a one norm, and then the norm of the gradients is measured with the infinity norm. So you get rid of the dependence of d in the norm of the gradients. Before, for OGD, your Euclidean mirror map, squared Euclidean norm mirror map was strongly convex with respect to the two norm. And now the dual of the two norm is again the two norm, and then you get the dependence of d and the gradient, even though you bounded the infinity norm by a constant. And that's why you get this d dependence here. And you get back a mild dependence on the dimension in the diameter. It's not really the diameter, but the distance between from any point in the simplex and the initial hypothesis, in the initial model. Okay, so this is what I wanted to say in, I just have half an hour, pretty good. Wanted to say with respect to this interplay between the geometry of decision space, the choice of the mirror map, and the analysis of online mirror descent. I hope you got the gist of this argument. And again, the mathematics is reasonably simple. Of course, you can play with norms. You can say, why? Okay, why should I use a Euclidean norm? I can use the squared p norm as a mirror map, where p is now is any coefficient. To leverage the geometry of the model space in this setting, it is possible to replace the Bregman divergence with the Wasserstein metric. Wow, so we are getting to very, very difficult questions here. Well, this is actually active topics of research. The answer is yes, to some extent. I am not really familiar with that branch, but there are papers that actually do online analysis using Wasserstein metric, which is another way of measuring distances between the distributions. So the answer is partially yes, but it's not fully understood yet. Okay. So, okay, if you use the p norm, just in passing, I can tell you that, well, if I choose p of the right size, okay, there's another question. What if we replace the constant learning rate with adaptive learning rate? Okay, I cannot use online mirror descent with exponential, with the negative entropy mirror map and variable time learning rate. The analysis just doesn't work, right? So you have to use different algorithms for doing online. So online mirror descent is not the online algorithm, only online algorithm for solving online convex optimization problem. There are a few others. And these, some of these accommodate variable learning rates, even if you work with the exponential, with the entropic mirror maps. Okay. So, right, so in somehow you can, another solution to the same question is that if you use a p norm as a mirror map with the p tuned according to this quantity, which depends on the log of the number of dimensions, then essentially you get a bound similar to entropic mirror map, but now you don't have the tuning problem because you are not using an entropic mirror map and a Kubla-Libler relative entropy Bregman divergence. So there are sort of ways around, different workarounds to this tuning problem. Okay, and then you can, this has been generalized a lot. I'm just showing you a few examples. Okay, so now I want to tell you other things. Okay, I want to tell you just a very few words about AdaGrad. AdaGrad is an algorithm which is used a lot, and it is in stochastic optimization because it's nice and effective, and it has a nice property which is the algorithm is scale invariant with respect to coordinates. So it's independent with respect to rescaling of the coordinates. And this is useful in neural network training because the range of gradient components varies a lot across layers. So you would like your algorithm to be to sort of be oblivious to the scale of the gradients, to the scale of the gradient components. Okay, so in order to get this independence, we choose a decision space, an hyperrectangle. This makes sense, right? And the idea here is that this is a way to show you the flexibility of this mirror descent framework. So what we do here, we run an instance of mirror descent with Euclidean mirror map in a separate independent instance for each coordinate. So we are in an hyperrectangle as a decision space, so it makes sense to do that. And we can just write the gradient descent with projection with a very simple update, which looks like that. And we can choose the learning rate exactly as requested by our general online mirror descent, but we now choose a learning rate which depends on each single coordinate, because we want the algorithm to be to adapt to the scaling of each component of the gradient. So now you see the learning rate depends on the scaling of the gradient components for each component I. Okay, so now we are running these instances of online mirror descent, one in each coordinate, and we are doing updates, one for each coordinate. How can we analyze the regret of this thing? Well, it's pretty easy, because we can just, you remember, we actually, when we analyze regret, we do this linearization step. So we transform the convex problem in a linear problem. And once we have a linear problem that we want to analyze, it makes sense to look at one coordinate independently from each other and to sum them up. Okay? So if we sum up the regret components in each coordinate, we end up with the regret bound of this form. And we can, okay, again, so this has to do with the fact that I linearize my regret by exploiting the convexity of the loss. So I transform a convex problem into a linear problem. And once I have a linear problem, life is easy, okay? Because I can play a lot with different tricks, okay? So I can compare this sort of a composite result with the bound I would have gotten using OGD on the same hyperrectangle. And for simplicity, let's just work on a box, on a hyperbox. So the diameter of this hyperbox so it's a hypercube of side 1. So the diameter is square root of b. And now I can do my OGD update followed by projection onto this hypercube, and I can choose the learning rate as it should be chosen. And now I can. This is what I get by running OGD, and just by plugging in the bound I had before. And this is what I got by using my AdaGrad with independent tuning for each coordinate. And this is, by Jensen's inequality, it's easy to see that this is always smaller than that. So if I work in an hyperrectangle, it's always useful to use a tuning, a more powerful tuning, which depends on the individually on the gradient components. And in addition to that, I get an algorithm which is invariant, which simultaneously adapt to individually to each component of the gradient. So now if I rescale, so the idea is that if I rescale a single feature, right? So by rescaling, correspondingly rescaling the gradient, the algorithm will just be oblivious to that, because the learning rate will adapt to this rescaling. Okay. So that's the idea. Very good. So what is the time here? The time is okay. So I have some other slides here. Okay, I will go quickly on these other slides because I want to get to the contextual bandits and spend a few words over there. So this linearization of the regret I told you about has a side effect, is that basically I lose most information about the curvature of the loss. And this, unless I do this linearization with a little bit more care, okay? So maybe if I know that my losses are strongly convex, rather than being simply convex, maybe I can get a better rate. And exactly this happens. So if I run online gradient descent, so Euclidean mirror map, but if my sequence of loss function are strongly convex. So now losses are strongly convex, not only convex. And basically, I have to change a few bits in the analysis, and I have to use a more aggressive learning rate. And then I get a regret which scales logarithmically with time rather than with the square root of time. Okay, so I get an exponential improvement in the regret whenever my loss functions are strongly convex rather than being simply convex. And this is important because every time you want to run a stochastic gradient descent on some regularized objective, like again, support vector machines or something like that, you actually, when you do your stochastic gradient descent conversion to online, you actually end up with a sequence of strongly convex losses. So when you run online gradient descent for minimizing SVM, you will converge to the minimum of your SVM objective at a faster rate because you are exploiting convexity. Okay, so I am skipping other things here. I'm skipping more things here because I want to give you a bit more yes, space. So yes, yeah. So let me say a few more things that are a bit more general and could be interesting. So I'm sorry for skipping these slides. It's always bad skipping. It feels kind of bad skipping slides because it's, oh, all this knowledge I lost because the speaker, the lecturer was just too slow. Yeah, I'm really sorry, but it's sometimes it's better to understand very well what I managed to say and skip a few things. Okay, so I want to mention this because this is a difference between a real difference between statistical learning and online learning, right? So we motivated online learning by saying, look, you know, you want to deal with data streams in an efficient way. So you want to do incremental updates rather than, you know, global optimization over the training set. Fine. And what's the advantage? Oh, well, you can analyze the streams that are not IID, but they're actually deterministic. Wow, that's cool. So maybe I can accommodate the non-stationarities, right? However, in all the regret analysis I showed you, at the end of the day, I'm always competing with the best model in my class. And this is a bit underwhelming, right? It's a bit disappointing because you're selling me online learning in order to be able to deal with non-stationarities. But at the end of the day, your regret measures how good you are with respect to the best single model in your class. But wait a minute, if your data is highly non-stationary, which means that the loss, the sequence of convex losses that you're observing is a lot different one from the other, then there's not going to be any single model in your decision space that is going to perform well on this loss sequence. So it's, I mean, you're winning against a bunch of weak people, right? None of them is good. So even though if you're bad, then you're looking good because you're competing against bad models. So if data is truly non-stationary, there won't be any single good minimizer in your model class, right? So basically, the cumulative loss of any of your models in your model class is going to be huge. So maybe we should rethink the notion of regret, right? So you should have a notion of regret which is more robust with respect to the fact that the best model in your class can change because you're tracking a non-stationary stream. And this comes from what has been known as dynamic regret. And in dynamic regret, you're not competing with a single model, but you are competing with a whole sequence of model, one for each time step. Yeah. So now I say, oh, this sounds real now. Okay, so we're now competing on equal grounds. I have an arbitrary sequence of models. Maybe this is just the best single model for each single loss function at every time step. So first of all, you know, at first sight you say, well, I don't stand a chance. You know, I'm competing with an objective which can optimize every single function, every single loss function. And wherever I don't know this stream of loss functions, I just see them one after, I just see the gradient of each function after I made my decision. So how can I stand a chance in this case? Well, the idea is that there's going to be some complexity parameter here. So essentially, the regret is going to scale with an extra parameter that is accounting for the fact that this is a tough playground. So basically, instead of depending only on the diameter of your decision space, you're also going to depend on the trajectory of your model, of the model sequence you're trying to track. Okay, so you have some non-stationary phenomenon. This non-stationary phenomenon corresponds to some sequence of loss functions, and this some sequence of loss functions corresponds to some sequence of good models that tracks well that sequence of loss functions. So now I have this complexity parameter which says good, you know, if the sequence of good models is not covering a wild trajectory in my model space, then maybe I may stand a chance here. Is that clear? This sounds pretty reasonable. So this sounds like a reasonable price I should pay in my regret bound because I'm now really looking at a non-stationary problem. So I'm really competing against non-stationary objective. Okay, notice that this sequence is completely arbitrary. So my regret analysis here, which I won't cover for lack of time because it's a bit more complex, it simultaneously holds against any sequence of models, including the best possible sequence for the given sequence of loss functions. I can prove lower bounds that have this form, which tells you that, look, if you want to do this, if you want to compete, then it's not the end of the world. You have to have a dependence that is slightly more articulated. It will include this additional complexity parameter. with its complexity parameter is 0, so we fall back to the original definition of regret, and we fall back to the standard lower bound here because pi is 0. Okay, and that's our standard lower bound. And it is possible to match this lower bound. Unfortunately, there is no quite simple solution here. So what you have to do is a two-tier solution. So basically, what you want to do is you want to run instances of OGD, each tuned to a different value of this pi. So it turns out that you can adjust OGD. If you knew the value of pi in advance, then you can adjust your OGD and tune it to this value of pi and get an upper bound which looks like this lower bound. The problem is that you have no idea of pi, and you want simultaneously compete against all pi's. So what you do is you run a bunch of instances of these OGDs, each tuned to a different value of pi. And then you use a hedge, which is prediction with expert advice algorithm, to aggregate these different instances of OGD. So this is a kind of way of mixing the two lectures here. So we are using this idea of prediction with expert advice, and we are using instances of OGD as actions that we choose at every point of time. So we are aggregating these actions using these exponential weights. But exponential weights is just at the top level. At the lower level, OGD is doing the actual work. So this is kind of interesting and fascinating. And it looks like all these things are pretty modular. They can be combined together without too much of a hassle. Okay. Other notion of regret, which is adaptive regret, I'm going to skip it. And I'm telling a few things about contextual bandits. Okay, so what is contextual bandits? Contextual bandit, it's what you happen to deal with if you want to do, ads or recommender systems for real. Because in reality, everything has features, and you want to use them. So actions in bandit problems and features, because they are ads, they are items on sale, so they will have features. So you can think now of a problem in which you want to put together the online convex optimization setting of online mirror descent we saw in the second lecture, and the partial information setting we saw in the first lecture with the bandits. So you want to put them together so that you will have a way of dealing with features in a partial information setting. So the idea here is, again, is an online protocol in which you, at every time step, you observe a finite set of contexts, which are your feature vectors. So you have a bunch of ads that you can, and you can display one of them. So you choose one ad to display based on the features, and you get some reward. Okay, for contextual bandits, we're talking about rewards, just for a change, instead of losses. And what changes here is that we are assuming a latent linear model where you have some we have a linear model with latent parameters, and you have a noise with zero mean and bounded variance. So this is now we are putting a little bit of probability in the model, okay? And so basically your reward will depend linearly on the features according to a latent vector of parameters that you have to learn, which is the same, a constant but unknown. But this set of context is just arbitrary and deterministic. So that's the online aspect. And this is a little bit of probabilistic modeling, which I introduced. And now, is linearity in features a simplified assumption? Absolutely linear. That's a simplifying assumption. You can use generalized linear model. You can play with it, but you have to make some assumptions. Otherwise, it's hard to deal with features in an effective way. So this is assumption that pays off because you get an algorithm that actually works in practice. Okay, this is a notion of regret. And because you have this fixed set of latent parameters, you're changing a little bit. So now the regret is the other way around. So because you are looking at gains. So this is the expected gains of the sequence of choices made by the algorithm. Okay, so the reward, the expected value of the reward is just this inner product because ZT is zero mean. So this is the sum of the expected rewards of the algorithm's choices. And this is the sum of expected rewards of the Oracle algorithm that always chose the best context, the best option in the set at time t. Okay, right. So how much time do I have? Not much, 10 minutes. I have to say
Like 5 more minutes, and then we have some time for questions left.
Okay, good. So how is this working? Okay, this is a again online analysis, but it is a bit, we don't do the analysis, we won't have time, but I will give you a few ideas here. So the idea is here that we have a linear model, okay? A linear model with noise. So it's a good idea to use a regularized least square estimate to guess the parameters of the latent model. You know? So it's a linear, so regularized least squares makes sense. Yeah, it's a linear model with noise, so what's best? And so this is the regularized least square estimate that you build using the choice you made in the past and the rewards you obtained. And V is the covariance matrix of the choice you made in the past. Okay. And now it turns out that you can prove that a property of your regularized least square estimate, basically that the latent vector will belong to an ellipsoid centered on the regularized least square estimate, where the metric of the ellipsoid is defined by the covariance metric of your past choices, and the radius is given by the parameters of the problem: time, number of dimensions, variance of the noise, and the norm of the Euclidean norm of the latent W. And here's the picture. So basically, this is your regularized least squares. This is your ellipsoid, confidence ellipsoid. So you know that the latent parameter is over here. So how would you want to choose here? So the idea here is that you want to, if you have some context that you want to decide whether you pick it or not. So this is one adds in your context set that has some features as a point in your space. So the way you want to do it is you want to pick the context X that maximizes the inner product between all of your candidates in the ellipsoid. So essentially, this the ellipsoid tells you all the possible is a confidence. It's a multidimensional confidence interval for the latent parameter. Okay, so all the points in the ellipsoid are are good high probability candidates for the latent parameter. So you're choosing the one that is maximizing the probability of reward. This is the one that, this is the logic you work with. Okay, so among all consistent parameters consistent with the past choices, you're choosing the one that's maximizing your expected reward. And this turns out to be an easily solvable optimization problem. And what you can prove with the choice is exactly something, again, which scales with the square root of time and with the linear in the number dimension, and then you add an additional logarithmic term. And I really would like to stop here at this point because it looks like I'm gonna run over time. So let me just say one word of comment. so basically, so you see that this online learning, online convex optimization is kind of flexible and versatile. And this last application was a bit hybrid because I introduced the probabilistic model, but I could, the analysis was still done in a completely online setting because the set of contexts that the set of feature vectors that the algorithm is observing is a completely deterministic and arbitrary sequence, okay? So there's still some flavor of the original online analysis, although the actual analysis of the regret is a bit different because it has to take into account the probability in the linear model. Okay, thank you so much for your attention. I hope this was useful. I gave you, a few glimpses on a very large world that has different facets. There's a lot more to be learned, not only in the skipped slides, but also in the stuff that I didn't include. But I hope you got some interest in the study of this field. Thanks a lot for your attention.
Thanks a lot for your lecture. So are there more questions for Nicolo? So there's something.
Can you say something? Okay. Can you say something about online learning with losses that are not local, depend not only on the current stage, such as calibration? Okay. So so a lot of mileage in the analysis of online learning is obtained by the additive structure of the regret. Okay, if you lose this additive structure, then things become a lot harder, and you can, of course, in some cases, so a calibration is a good example. You can still do, so somehow calibration is telling you a different thing. It's something which is studied in game theory, and you're really caring about convergence of your actual decision to some subset. Okay, so your WT has to converge to some subset, and well, I'm actually making a little bit of. Okay, let's stop here. I don't want to make more confusion. What I wanted to say is that you can give up the additive structure of the regret, but to very little extent.
Right.
And,
so there are two more questions.
Can you say a little more about optimism in the face of uncertainty? Yes, so this is a traditional way of studying, of compensating for lack of information. So we saw the incarnation of this principle when we studied the bandit case, because we gave a loss of 0 to all the action whose loss we didn't observe. And in that case, we replaced the uncertainty with optimism, because we said, okay, we didn't observe the loss, let's say 0. In this case, this is another incarnation of this principle, is saying that, okay, I'm just taking the option that looks better among those that are plausible, that are within my confidence ellipsoid. What is the reason? Okay, if you have a bunch of, the idea is that if you have no knowledge, so you should definitely choose the option that looks best given the current knowledge that you have. Once you take into account the variance in your decision, okay? So optimism in the face of uncertainty means that I should okay. Let's see. It's harder to explain this in a few words, but in a sense, I have two objectives here. For one hand, I have to do exploitation. So I have to choose the the option that has the best chances of delivering the highest expected reward, for instance, in the linear bandits case, in the contextual bandits case. On the other hand, I have to control the variance, right? If some option on which I have very little information looks bad, maybe it just looks bad because I have little information about it. So I have to reconcile these two objectives, control the variance of my options in order to have the least uncertainty about them, and maximize the expected reward, because at the end of the day, I want to control regret. Optimism in the face of uncertainty is a way of combining these two things in a single objective. So I would like to choose the action that maximizes both the promise of a good reward and the fact that I want to reduce the uncertainty about my estimates. Wow, it's it would deserve a lot more.
Maybe we can take one more question. You can pick one, and the other ones we leave for the round table.
Do you actually need norms to do the analysis, or rather metric distances? Is Bregman divergence more related to metric spaces? Okay. What I need a linear space. I need a linear space with the notion of norm, because I typically want strong convexity with respect to a norm. So I need the linear structure with norm. So this is definitely the least amount of structure I need in my spaces. This was a question that was also asked a little yesterday. Maybe can I answer this question?
Yeah, sure. I mean, we have a break now, so if you want to go a bit over time, I think that's...
okay, maybe I will just reply to this one. I think this is the... What is the role of statistical learning theory to modern machine learning? For instance, deep neural nets. Is the uniform convergence bound usually used in learning theory sufficient to explain the generalization of deep neural nets? If not, what is missing? Okay, so the answer is no. The uniform convergence bound is not enough, is not sufficient. And what is missing? Okay, the good generalization abilities of deep learning is the outcome of three ingredients: the structure of the neural network, the distribution of the examples of the data, and the algorithm that you're using to find the local minima of your objective function, of your loss function. The interplay between these two ingredients delivers good generalization if done properly, if you mix the ingredients in the right way. So it's not, so generalization, this traditional generalization bound somehow say, okay, let's assume I minimize my error, my training error, and just focus on the structure of the model. So it's just if, okay, it doesn't really important the algorithm they're using. It's what is neither the algorithm I'm using, not the distribution of the data. The only important thing is the structure of my net. Actually, this is not sufficient for explaining the good behavior of neural networks in deep learning. You really need to take into account the fact that your data have a certain distribution, and you're using a specific algorithm to minimize your training error. And this is very complicated because it essentially needs a lot more complicated theory to account. I'm not an expert in the generalization of deep learning, but there's very good people that are working on it, and there are lots of new results. But you really need a new generation of analysis to account, to explain the generalization power of deep learning. Okay, maybe I will take the other questions offline because I also have another meeting coming up.
All right. So thanks a lot for the lecture. Thanks for the many questions from the audience. And keep in mind that you can also back the speaker on Mattermost, and they will answer your questions.
Okay.
And yeah. And there will be a roundtable discussion with Nicolo, so I think there will be plenty of time for discussions.
I'm sure people are dying for it.
Okay, so thanks a lot, and
Thank
have a good
you.
day, everyone.
Thanks. It was a
Bye.
pleasure. Bye-bye. Bye.